Hello. Now today we're gonna do a PWM implementation that we can run actually a servo motor through a timer, and let's just see how that works with an ARM processor. We are just connecting an ARM CortexM4 processor to our motor. I'll show you the setup in a minute, and let's just go on with opening up our STM32CubeIDE first. Make sure you start up a new project from new STM32 project at the top. From the interface, you select your device that you would like to run with. In my case, I select mine and click next and choose a file name. Just give a name. So I call it Servo PWM. It loads up an IOC interface so that we can do our implementations faster. Here we're using mostly HAL libraries, but in classroom we're also looking into the real register implementations of how these actually work. So we have the pinout interface in front of us. The first thing that we do always is we start up in the sys the debugging session. So debugging is done through a serial wire, so make sure that a serial wire is selected in the SYS selection. So once that is done, we can go ahead and select the timer. We'll be working with timer 2, and the clock source is going to be an internal clock. Now, as you see, we have the configuration for the settings for the timer 2. We're going to be setting up the prescaler and the counter period. We have a GPIO which is already predefined for channel 2. If you select channel 2, the default channel is going to be through PA1 connection. It has to be made from that part. Now I don't really have to do that. I can change that PA1 to something else. The reason I did that because I ran into some problems with PA1 being coincided with some other interfaces. So I deselect this by setting it into a reset state and pulling I use PB3 as my output that I connect to my motor. So I choose here timer 2 channel 2 and I select PB3. As you see, it's yellow color over here. That means I haven't made a selection on channel 2. So I go ahead and select channel 2, PWM generation channel 2 is selected. As you see, when you did that, your line is now becoming green, as you see here on your pinout view. That is fine. And now what you have to do is you have to set up your prescaler value and your counter period values. Now, for that purpose, you have to go into the clock configuration and check out which clock that you're running with. According to this figure, I have my high-speed internal clock over here is connected as 8 MHz. That is being transferred into the system clock as 8 MHz, and my output timer clock is again 8 MHz. So I have 8 MHz clock on my timers. I know that I'm running with 8 MHz, fine. Now I need to set up some prescalers, and let's see how that is done. So let's do some calculations over here. I have 8 MHz. That is, I need a prescaler value to bring this down to a lower frequency. So I just divide this by 16 to make it 500 kilohertz as my frequency. As you know, T is equal to 1 over F, and my period that is going to be associated with that is going to be 0.02 times 10 to the power minus 3 for my period. Now that is basically 2 microsecond. Now I know each tick for my period is going to be 2 microseconds, but I have another constraint, that is 50 Hertz is needed for the servo. So it needs 50 Hertz that is running like that. Okay, and then for each duty cycle I just need to be on for a certain amount of time. Of course, not the duty cycle for 50 Hertz, but some smaller proportion for that is going to be used for the angle rotation. So it's not going to be a full range, but it's going to be a shorter range within the 250 and 1250 counts per that counting period. So I'm not going to be counting through the whole time of 50 Hertz. I'm just going to be counting only for some portion of that 50 Hertz. So if we assume that that is going to be 10,000 counts, I need less durations for those counts. And I just need to give those amounts in as a HAL library operands, so they can be calculated automatically. But I just need to find this number over here by dividing this 1 over 50, which is 50 Hertz is going to be my t, desired t, that's going to be 0.02. And if I divide 0.02 by 0.002 times 10 to the power 3, that is going to be 10 times 10 to the power 3, which is 10,000. So I need this amount basically. I just need a smaller portion of that to be available for my counting duration. But I just need to enter this as my counting period in my calculations. So I just need to do that. I come back to my interface, STM32, and I type in here for counter period 10,000. My prescaler is going to be 16 minus 1. Oops. 16 minus 1. Now that is done. I just need to enable the auto reload preload as enable. I did that. And I'm done. I just save this part. I generate the code necessary for the code to run automatically. So I need to verify some lines are being inserted fine. So I just have to go through the code step by step a little bit. I made sure that my initialization for timer 2 is done. GPIO initialization is regularly done anyway. So we need some other line in between user code begin 2, user code and 2 over here. That's not done automatically by STM, so we just have to insert that line that starts up the PWM here. HALTIM PWM start HTIM2 has to be inserted as an extra line. So whatever that you put inside while one statement is going to be run repeatedly, and what I prefer to do is to test the upper bounds and the higher bounds of my rotation. So I just insert that those lines inside the while statement. I go to the lower range, I move up to the higher range. So let me show you the code over here once again. So I assume my lower range is 250 and my higher range is 1250. So I go between those ranges by giving a delay in between those angle rotations. Okay, so this is going to be done over and over again. There's nothing else at this moment, so I just compile the code. And afterwards, once this is compiled fine, I'll show you the output, how it looks like, and I'll show you the scope output as well. I'll wait until it is compiled without warnings and errors, and let me just upload it to my device. Make sure your device is connected. Just have to turn it on, and then you just have to download it onto your device. Yes, on the board, once I have made the connection from PB3 to my servo, my servo is moving back and forth between its two limits. While it's doing that, I can observe the output from the scope that I'm actually in between those two limits in PWM generation. Yes, we just seen that we're experimenting these two limits, but let's just go through the whole cycle from the lower range to the higher range. That's also a good exercise to do, and for that purpose we have to write a loop statement, for statement for that. So I use a parameter of x to move within that range. As shown, I have a loop from the lower range to the higher range, and just give a short delay in between those hops, in between those rotations. Let me compile that as well and see how that goes. Yes, it also worked fine with the compilation, and let's just see how that is actually running. Okay, so I just started the program, and as we see, we're scanning the range from the lower end to the higher end. The inset stability is due to a voltage source, the current being drawn, so I just connected a power supply to that for a current to solve the current problem. Now it's working better, as you see. So let's just observe scope output as well here. Thank you for watching. That's the end of the presentation for Servo PWM. See you later. Bye bye.